Thank you, Ed, and thank you to all of you for being here today. Starting today, our ability to understand dark matter, dark energy, planetary things will grow even faster than ever before.
The follow video is 1 minute long, and we will first enjoy it without any comments. Then we will replay it and I will comment. Enjoy.
Hello people, another week more in the NuSTEAM program and we are almost done. Next week we are going to present our final projects as I mentioned last week, and my project is about the QCD phase diagram and how the state of matter changed from hadronic matter to the deconfined quark-gluon plasma state of matter. This project will be presented next week and I'm a little bit nervous since it's going to be in front of our professors and classmates, but I'm pretty confident about it. For this week, we started with the exciting first reveal of images captured by the Vera Rubin Observatory in Chile over 10 years. It is the largest digital camera ever built, which can capture extremely detailed images of space in Chile, and it can also capture moving objects like asteroids, supernova, and objects far away. So it's 3200 megapixel camera and can produce 20 terabytes of data per night, and the image image is so amazing that you can see the billion of galaxies. So for seeing the complete image, you need a football stadium full of TV so we can reproduce the complete image. This observatory creates a website page where you can see the complete image. I will put the link on the description. Anyways, this week was exciting since we learned more branches in physics, not only the nuclear physics and heavy ion physics part. We saw astrophysics, medical physics, and also quantum computing. And Dr. Belwi did an excellent job explaining all these complex topics. The first thing that we explored was our solar system. When we ask what we get from the sun, the correct answer is energy, but not light or heat specifically. The sun doesn't create energy. It converts one form, the chemical and nuclear energy, into another form in electromagnetic and radiation waves and also heat. With the fundamental equation, we can unify every electromagnetic radiation, for example, the radio, the TV signals, the cell phones, microwave, and also visible light. So the sun is the primary energy source for life on the earth, and it converts the nuclear energy into electromagnetic radiation across the entire spectrum, but specifically for visible light. The sun is made of different shells of gas with changes in temperature and pressure. It has a very strong magnetic field since its interior is ionized, and because it's a gas body, it rotates differently at the center. So for example, in the earth, the magnetic field in the earth is like this. So this magnetic field is created by the liquid iron in the core of the earth that is moving constantly. So this produces charge, and for that this produces a magnetic field. The sun maintains its size and shapes through a balance between the outward pressure, it means the energy generation in the core that creates the pressure wanting to blow the sun apart, and also the inward pressure, the gravity that pulls all the material towards the center. So this creates a stable dynamic system that has maintained equilibrium for billions of years. The sun is made up of 90% hydrogen, 7% helium, and 3% everything else like oxygen, carbon, iron, sulfur, neon, nitrogen, etc. So the sun fuses hydrogen into helium through a process. So first of all, we have the hydrogen fusion that we know as the pp chain, when two protons combine the form of helium and it releases energy. Then we have the CNO cycle, the carbon, nitrogen, and oxygen that catalyze the hydrogen fusion. And we have the helium burning, that is the process that creates carbon that continue fusing elements up to iron. So is the element 26. Beyond iron, fusion requires energy input rather than releasing it, which is why the sun cannot produce heavy elements naturally. So all the elements heavier than iron, for example the cobalt, the nickel, the copper, silver, gold, cannot be formed by normal stellar processes. And so this process requires extreme conditions like a supernova or a neutron star merge. So where did these heavy ion nucleus elements come from? We don't know actually. The sun is about 4.6 billions of years old and is in the middle of its stable hydrogen burning phase, and it has approximately 3 billion years remaining in this stable state. So after the sun exhausts its hydrogen fuel, the core will contract and heat up, the outer layers will expand in a red giant phase, and eventually the core, it will become a white dwarf. So our sun is not massive enough to become a neutron star or a black hole. For a neutron star, we will need about 1 to twice the mass of the sun. And that's pretty much it for week 5. Sorry for the delay in uploading. I've been super busy working on my final project, but I really wanted to share everything I learned this week. Thanks for being patient, and I hope you enjoyed the video. I'll see you really soon for the final week. Bye!